Zoom recording. The way I want to launch in this morning is with an example from the textbook. It is example 9.5 from section 2 on calorimetry. And the example is a story of a couple of liquids, hydrochloric acid and sodium hydroxide. And both of these liquids are at the same temperature. And we're going to put them in something that insulates really well, like a coffee cup. And we're going to watch the temperature of the liquids in the mixture when they're combined go up. And we can determine from that the approximate amount of heat produced by the reaction. Now, the liquids are hydrochloric acid and sodium hydroxide. Hey, what do we know about mixing hydrochloric acid and sodium hydroxide? What are the products of that? Okay, sodium chloride, I'm going to totally take out and just drop it down there as aqueous salt. That's fine. I love that you said hydrogen hydroxide is the other product. I absolutely adore that because that was how I got taught to recognize the products of these reactions when I was coming through my high school chemistry. Just to write this down as HOH. But hey, HOH is the same as H2O. What's another name for this hydrogen hydroxide? Water. Sure. Okay. This is a neutralization reaction. Okay. Combining an acid and base. And it's significant that I'm combining the same volume of the same concentration of these guys. Because if I got the same volume of the same concentration of two things I'm reacting 1-to-1 ratio stoichiometry wise, well, what's going to be the upshot of that? What's going to be what I'm reacting? I'm going to be reacting equal moles of each of these things. So I'm using everything up in the reaction. Which is one way I can know that the reaction is happening as efficiently as it possibly can. Now, has anybody done this before? Has anybody been in a laboratory setting? And those of you who are on Zoom, feel free to acknowledge it in the chat if you have. But have you been in a lab setting where you have taken and intentionally added some strong acid to some strong base? And you've seen what happens? ? 'Cause I can spoil it for you if you never have. Visually, it looks like nothing. It looks like you're taking a water-like liquid and you're adding it to a water-like liquid and putting them together, and you're getting a water-like liquid out. I mean, when it's hydrogen chloride and sodium hydroxide, you don't even get any fizz out of the thing like we're going to see this afternoon. Okay, it's just there. But what was relatively cool does warm up a good bit. Okay? And so when we actually say in the problem, what's the approximate amount of heat produced by this reaction? What are we actually pointing towards? What equation can we use to talk about the approximate amount of heat produced? Y'all are pretty reserved people. Please do not feel like you have to be reserved people in this room. You are among friends and the people on Zoom can't hear you. What equation do we use to find an amount of heat produced? I'm going to be telling a story like that for heat capacity, but I don't have a heat capacity expressly in this problem. There's nothing indicated about the calorimeter's heat capacity. So it's not that story I want to use. Give me a different equation that has Q as the left side. Go. Q equals M times C times delta T. Mass times specific heat times the change in temperature. That's a good starting place for what we want to accomplish. Okay. But there are things that are not given to us directly as we're going through this particular solution. Okay. The first problem in hand is, what's the mass? How much mass of a stuff is changing temperature? And it's worth it at this point to actually back ourselves up a little bit more and to ask precisely, what is the majority of the stuff here that is changing temperature? We're given a chemical reaction, but the chemical reaction can also become something we get very lost in. And we can lose sight of what the majority of this mixture we're putting together is made up of. Need a hint? What does AQ stand for? Aqueous, absolutely. And what does an aqueous solution have as its solvent? What's doing all the dissolving in an aqueous solution? Water. The majority of the stuff here in this reaction is water. There's much more water than hydrochloric acid in the solution. By the way, if you actually get water running around in a container like this, has anybody looked into what the actual molarity of water in a container like this is compared to the molarity of the 1 molar hydrochloric acid? That's not a pipsqueak concentration, 1 molar of hydrochloric acid. But what the concentration of water is alongside that, it's on the order of 55 molar. In any aqueous solution, water's running around 55 molar, and you have to be at a really high concentration of other stuff to compete with the amount of water that's running around. The overwhelming majority of an aqueous solution is water. And we can treat the overwhelming majority of this aqueous solution as water as we're going through and we're solving for specific details in the mass of the stuff. Okay? I'm taking 50 milliliters of the hydrochloric acid solution and combining it with 50 milliliters of the sodium hydroxide solution. How much total mixture am I going to have when those two are combined? It's 100 milliliters, sure. Okay. Well, what's the mass of 100 milliliters of water? How do I convert from the volume of 100 milliliters of water to the mass of 100 milliliters of water? What do I need to know about water? What property of water tells me how much mass it has per milliliter? Y'all on Zoom can use the chat too. I'm down with that. Grams per milliliter, mass per unit volume. What am I talking about? I've always believed this is where you really learn Gen Chem 1. Because I've gone over this many, many times before, but it's only when you get asked and you're got the sick feeling in your gut says, he says mass per unit volume. I've heard of that before. What does that actually mean? And that gets written and you go, oh my God, I should have known that. Anybody know the density of water? It turns out that the density of water is a constant. It's something that we can use over and over again. And it is the reference point for all other densities. To 3 significant figures, it is exactly 1 gram per milliliter. So it is entirely appropriate if you have not just 100 milliliters of water, but 100 milliliters of any aqueous solution to approximate the mass of that aqueous mixture. As 100 grams. 3 significant figures of accuracy. Everybody see that? Everybody see what I just did there? We'll come back to estimations like that again as we go through solutions for other problems. Okay? And it turns out the specific heat of the aqueous solution, 4 significant figures, we can treat as the specific heat of water. And what's the specific heat of water? And that's the point where you know somebody's been messing around with the homework. Because that's gotten used a little bit in the homework, hasn't it? Okay? And oh, by the way, what's delta T in this story? Yeah, it's just 28.9 as a final minus 22 as initial. Delta T is equal to 28.9 degrees C minus 22 degrees C, 6.9 degrees C. Hey, we can compute a heat that is absorbed by this water in the solution. Q absorbed is equal to M times C times delta T, which is 100 grams from the mass of the aqueous solution, times 4.184 joules per gram per degree Celsius from the specific heat of the aqueous solution, times 6.9 degrees Celsius from the temperature change of the aqueous solution. And I can punch that into my calculator, 4.184. I need 100 grams of that. I need 6.9 degrees Celsius of temperature change. And I've got 2 significant figures in the temperature change. I'm limited to the 10th place on the temperature change. So I'm really limited to the 10th place in the Q absorbed, 2,900 joules. If you put 2890 or 2887 into sapling, sapling probably won't be mad at you. Sapling's not bothered with extra significant figures running around. Okay, questions? I got one. I've just computed the amount of heat energy that was absorbed by the aqueous solution. It's absorbed by the water. It dissolved the hydrochloric acid and sodium hydroxide initially. That's dissolving all of my salt finally. Okay? That's not what this problem is quite asking. It's asking how much heat is produced by the reaction. Mathematically, if you were to represent the amount of heat produced by this reaction, it would get represented as Q released. If Q absorbed is 2,900 joules, what's Q released?
Is it negative 2,900?
Why would Q released be negative 2,900 joules? Because that's correct. What was our initial fundamental rule for calorimetry? That fundamental equation that guides everything we do in calorimetry. If you take Q absorbed and you add it to Q released, what do you get? 0. Q absorbed is the negative of Q released. And this is a piddly little arithmetic thing with a whole lot of meaning behind it. Okay? That solution of water that the reaction is happening in raised its temperature by 6.9 degrees. That's how we know that the surrounding solution absorbed heat energy. That heat energy had to come from somewhere. Where did it come from? Came from the chemical reaction right here. It came from the hydrochloric acid and sodium hydroxide present here. Okay? And I want to make sure this stands a little bit separate from the types of stories that we were telling when we were in class on Thursday. Because on Thursday, we were talking about physical things. We were talking about a coffee cup absorbing heat energy and that heat energy being released by water that was placed into it. We were talking about a hot piece of metal being placed into water in a coffee cup and the hot metal releasing energy and the coffee cup and water absorbing that energy. Okay? In this case, we're talking about a reaction mixture absorbing energy and the energy coming from the chemical change happening in the reaction mixture itself, coming from the chemical reagents, not from a specific physical thing, but from a chemical change. This is the type of problem where we want to get to. Not just making sure we can handle M times C times delta T well, because we absolutely want to make sure we can handle M times C times delta T well. But also making sure that what we can handle is the place chemically where the energy is coming from. Okay? Comments, questions about that? So the next place we need to go is a more complete description of energy that's going to guide us in towards this type of accounting for what goes on chemically. And where I want to land by the time we get in here on Thursday, excuse me, is I want to land to where we have a specific type of energy that talks to us about what happens chemically in a reaction mixture. Okay? I don't know why I stopped sharing. I need the whiteboard back. Okay, I'm going to type for a bit. Let me know if I'm typing too fast. Sometimes the typing happens in such a way that it goes a little bit faster than people can write down. There we go. Now, remember those sign conventions I put in front of you when we met on Thursday for the heat energies that we were studying? This is a little restatement of those, and it's something that I'm doing a little bit more precisely. When Q is greater than 0, that is when Q is positive, we're talking about heat being absorbed by the system studied. And when that system is a physical system, that is when I can identify something tangible in the system that can change temperature, and Q is positive, it's all likelihood that the temperature of that physical system is increasing. Now, there are exceptions to that. We need to get into those exceptions as we move forward in the course. But based on what we've studied thus far, that's going to hold, and that's going to hold pretty consistent. So if Q is greater than 0, heat is absorbed. When Q is less than 0, heat is released. Thank you for that knee-jerk answer. And when Q is greater than 0, the temperature of a physical system is increasing. When Q is less than 0, the temperature of a physical system is man, y'all don't say that confidently. I heard. If you know something, be proud you know it. Okay? What you're doing as you write these sign conventions out is you're describing the first of our process energies. Now, I want to make you aware of a second process energy. And together with heat transfer, this other symbol will represent our two properties of processes that we're going to lean upon as we study energy transfer in physical and chemical systems. Now then, I think when we first started defining energy, somebody came up with that classic textbook energy. Energy is the capacity to do work. And what I expressly asked upon that was, well, what in the world is work? What does it mean to do work? The all-time classic example is me taking the chair that I'm sitting on in the lecture room and taking that chair and pushing that chair across the floor. I apply a force to the chair and I move the chair over a certain distance. Force applied over distance is one basic way to express work. Force is also not something I tend to talk a whole lot about when I talk about chemistry. If I'm going to bring force to the table, I need to bring force to the table in a different context. What's more, frequently when we launch into the study of thermodynamics, we don't like to talk about solids or liquids all that much, because solids and liquids don't show a whole lot of evidence of having received work in. Okay? So I push on a solid and it tends to retain its shape. I push on a liquid and I slosh the liquid everywhere, it changes its shape, but it doesn't tend to change its volume. Gases, on the other hand, are very convenient to study when we tell stories about work. And what I want you to do is imagine a gas in a piston. Something is substantially simpler than the piston inside a car engine as it strokes through and it transfers energy in the car engine. Just a simple piston where I've got a plunger in the piston. And this plunger is something that I can move up or down. And if I take that plunger and I press down on it, what's going to happen to the gas inside the container? This plunger is going to go down like so. And what happens to the gas if that plunger winds up going down like so? It's more compressed gas now. It's a gas where I've taken the volume and I've decreased it. And those of us who do the physics, what we do is we take our definition of work as a force applied over a distance. And we say by pressing this piston down some distance, the piston's got a cross-sectional area. By pressing it down by that distance, I've decreased its volume. I've decreased its volume by pressing down on it with a force, and applying that force over an area is applying a pressure to the gas. And I say that pressure times change in volume is the work done. Now, for the sake of my signs, I do one thing in addition. So I put a negative sign out in front of that. Work is equal to the negative of the external pressure applied to a gas system times the change in volume of that gas system. Now, why do I apply that sign? Well, if I take this piston and I shove down on the piston and I compress this gas, what is actually going to happen to the molecules within the gas? Before they were relaxed, they could just bounce here, bounce there, bounce everywhere. And they could just be dancing all about. When I compress it, these gas molecules get more excited. They're bouncing deeper and bouncing more vigorously and smashing into the sides of the container a little bit more, right? So by doing work on the system, I've actually increased the energy of what's inside that container, right? So let's set some sign conventions for work now, the same way we set sign conventions for heat. Let's frame it that way. Commonly, when W is greater than 0, W is positive, we say that work has been done on the system. Positive work is work done on the system. But by this example I've talked through here, by doing work on the system, by pressing down on this plunger, what I've done is I've made the molecules inside that system more excited. I've raised their internal energy, to use a term I'm going to define more fully later. Okay? So work that's positive is energy invested into the system. And when W is greater than 0, what's necessarily happening to delta V? W is 0, I compress this system. What happened to the volume of the system? It decreased. That's a little bit wonky if you just focus on numbers. If W is positive, delta V is negative. But in a gas system of this sort, if you're investing work into the system, you're doing so by decreasing the volume available in the system and increasing the internal energy of everything bouncing. Does that make sense to everybody? So let's do the flip side. When W is negative, commonly we refer to W as negative, representing work done by the system. And you can use your imagination to represent this. I've taken this plunger on this gas, I've shoved it down, I've invested energy into the system, molecules are bouncing around hither, yon, every which way. I let go of the plunger. What's going to happen to the plunger if I let it go in that circumstance? I've got all the molecules running around that thing, bouncing off of the walls. They're bouncing off the walls because I've held the plunger down. If I let the plunger go, what's going to want to happen? It wants to go back up. The pressure inside the gas is such that it's going to push the plunger back up. Well, if that happens, I didn't do any work. The system did the work. So in circumstances where W is less than 0, that represents work done by the system. It represents energy released from the system. When W is greater than 0, the volume of the gas system decreased. When W is less than 0, that must mean the volume of the gas system increases. Excuse me. These sign conventions are tremendously useful to keep the meaning of positive and negative signs straight in our head. Let's look at an example of how this, and this example does not appear in your textbook, nor does any example like this appear in your textbook. So this is a pretty important example as far as going through homework is concerned. Come here. Thank you for your patience while I try to make the text work. External pressure of 2 atmospheres, 3 sig figs. I'm going to talk about a volume of a gas system changing from 4 liters to 9 liters. And I'm going to ask what work is done in this case. And I'm keeping that general right now. As I go through this story, ask yourself and check yourself, is work done on this system or by this system in this scenario? Okay? Well, let's just use the equation. And the equation is actually straightforward enough to use right up front. W is equal to negative P times delta V. What's the P? Two atmospheres. What's the delta V? Why is it 5? Why is it not negative 5? It's not necessarily biggest to smallest. Final to initial. Always final minus initial. So let me just write it explicitly like so. Okay? Okay. Now, 2 things. Number 1, I've got a negative, and the negative doesn't get canceled out anyway. The negative is still running around. And this is going to be 2 times 9 minus 4, which is 2 times 5, which is 10. And what units are these in? Don't overthink it. Liters times atmospheres. So 2 things. Number 1, the sign is negative. Is the work done on the system or is the work done by the system? By the system. This is a system that is releasing energy in the form of work done. Second, what are the units of energy normally in stories that we tell like this? They're not liter atmospheres normally. They're joules. Yeah. Joules are our normal units of energy. Now, liters times atmospheres absolutely are legitimate units of energy. Okay? If nothing else is asked of you, you are absolutely allowed to say, well, the units of energy are in liters atmospheres, and that's all well and good, and I can just say that. But more often than not in sapling, when you get asked a problem like this, the blank that you're going to have to put the answer in is going to have joules on the right side of the blank. Liters atmospheres do convert to joules very directly. Okay? To 3 significant figures, 10 times 101.3 is going to be 1,010 joules. Everybody see how I did that conversion? It's a conversion that's going to come up a couple of times. Having this conversion factor in hand is going to help you out a great deal. Okay? The majority of the homework that comes up in the next set covering section 9.3 is homework that deals with this type of sign convention accounting. Okay? Recognizing when a sign should be positive or negative on a conversion of this sort. Okay? I really do want you to be aware of this type of thinking. Now, one other word from our sponsor here, real quick. Okay? The phrase process energy is very much my own. It is a phrase I'm going to use repeatedly when describing what work and heat are and how work and heat behave. Okay? There's actually a different phrase that your textbook uses in telling these stories. Let me get the image from the textbook in front of us here. Okay, this is where I was in section 9.2. I need to be where I am in section 9.3. Yeah, right here. Everybody see a picture of Mount Kilimanjaro in front of them? Mountain climbing tends to happen one of two ways, either by the shortest path or the most convenient path. The shortest path is the path straight up from the base to the summit. Now, for some odd reason, the shortest path to climb a mountain doesn't get used very often, because mountains tend to have very irregular terrain. And if you use the shortest path up the mountain, very frequently that path up the mountain gets you climbing up a severe cliff. And those don't tend to be very safe. So many of your paths up a mountain are winding back and forth. And you travel a great deal more distance on that winding path, but it's more efficient to get you to the top of the mountain. It doesn't get you climbing up too many straight up hill things. Okay? So distance traveled is a path function. This type of analogy also gets at why work and heat are sometimes, and your textbook is one of the places that this happens, sometimes work and heat are called path functions. Because how much work is done in a process, or how much heat is released in a process, very much is dependent on how that process takes place. In the case of work, there's a very good example that you'll work through, if I'm not intended, in the homework that gives you two different circumstances. One where the external pressure is the same all the way through, and one where the external pressure changes. And the result is two different amounts of work done, because the amount of work done is dependent upon the specific nature of the process handled. It depends on the path. Now, I call them process energies because they're properties of process. No one thing contains work. No one thing contains heat. Just like no one thing contains an amount of distance. The work done or the heat transferred is always a property of the type of process used. Okay? Now, they stand in contrast to state energies. It is very much possible for something to possess an amount of internal energy. If I have some amount of internal energy finally, subtract some amount of internal energy initially, I have a difference in internal energy. Internal energy is the sum of all the processes that are imposed on a given system that can change its energy state. Very roughly, we can describe internal energy of a system as adding up all the kinetic energies that individual atoms and molecules inside that system have. In equation form, we're going to define the internal energy change for a system in a given set of processes, like so. That any internal energy change in a system is the sum of the heat transferred into or out of that system and the work invested or released by that system. That too is a fairly straightforward equation. Okay? I change internal energy by transferring heat and doing work. Questions about that? Because that's an important enough equation that I want to give a name to it. Now, how many of y'all have heard the first law of thermodynamics before? The overwhelming likelihood that when you heard of the first law of thermodynamics before, you didn't hear of it in terms of internal energy change is equal to heat transferred plus work done. That is probably new. But you probably have dealt with a different formulation of the first law of thermodynamics. Alternately, you may have heard of the first law of thermodynamics in the context of the law of conservation of energy. What does that rule say? What's true of energy under the law of conservation of energy? Energy cannot be created or destroyed. Energy can only be transformed from one form to another. By saying delta U is equal to Q plus W, what I'm saying is any energy transferred into a system is absorbed by that system and is invested within the internal energy of that system, in the jiggling about of the individual atoms and molecules in that system. And it's a very subtle thing, but a very important thing, that whereas heat and work are always properties of processes, their sum is an energy that is path independent, that doesn't depend on the process, that I can compare initial and final values to. Put it another way. When we talk about heat and work as process energies, we're talking about them like the mountain climber on Kilimanjaro climbing the hill. He is likely taking a longer path, but it's a path that is most efficient to him. He's taking a longer distance traveled because he's taking a way up the mountain that winds back and forth. In the same way, a process energy like heat and work is dependent upon the way in which you do the transfer. And if different ways of making that transfer can get different amount of energies transferred. There we go. State energies, on the other hand, can be properties of a system at an individual point in time. Let me say that a little bit more simply. I can't have an initial heat and a final heat. I can't have an initial work and final work. You will never see me write delta Q or delta W. Heat and work are properties of processes. I absolutely can have a U initial. I absolutely can have a U final. I can talk about internal energy as a property that that system has at the beginning and at the end. And those changes in internal energy are independent of the processes. No matter how I actually make the change, if I wind up with the same U final and the same U initial, I have the same delta U. This distinction between process energies and state energies is super subtle, but it's critical to what I'm going to be talking about ahead as I introduce on Thursday a counterpart to heat transfer that I can treat as a state energy. On Thursday, when we get in here, we will introduce the concept of enthalpy and how we use enthalpy as an equivalent of heat transfer that we can manage as a state energy. That's our business for Thursday. I'm on time. Thank y'all. Bye, everybody out the room.